The first step in balancing any crankshaft is weighing the moving pieces. These parts would include the connecting rods, pistons, wrist pins, piston rings, connecting rod bearings, and oil ring support rails if used. Because we are using all new high-quality aftermarket parts, weighing one of each will suffice. Ordinarily, if using factory components, all of the connecting rods and pistons would be weighed separately. Setting the lightest of both aside, we would then remove weight from the rest of the pistons and rods to match the lightest, thus making all the moving parts weigh the same. Using higher quality parts that are guaranteed to weigh within a gram of each other allows us to skip that step, saving a good amount of time. In most cases, the piston or rod manufacturer will disclose the individual weights of every piece. I start by first weighing a connecting rod. Not only do we need the total weight of the rod, with cap and bolts included, we need to weigh the rotating weight, or the big end as many engine builders will call it. Another piece of information we will need is the reciprocating weight of the rod, or the pin end. So, after weighing the total connecting rod weight, we use an instrument to weigh the big end. It holds the rod in a way where only the half of the rod over the scale is weighed. However, there is a stand and a bushing to support the big end of the rod on the scale. The weight of these pieces must be subtracted from the value our scale gives us to achieve the actual big end weight. The reciprocating weight of the rod can easily be calculated by simply taking the difference between the rod total weight and the big end weight. Next, we weigh the piston, wrist pin, one set of piston rings, then the oil ring support rail. So why are we doing all this? We need all this information to calculate what the mass of our bob weights need to be. Bob weights are simply a two-piece weight that bolts to the rod throws of the crankshaft. They simulate the moving weight of all the pieces connected to the crankshaft. In reality, we are not balancing the crankshaft. We are balancing the rotating assembly of the engine. Okay, so we already weighed all of our moving parts. We're going to tell our balancing software what the weight of everything is, and then it's going to calculate what the bob weights need to be. You can do this by hand with just simple math, but we do it this way because I can save this and we can always refer back to it later. Total rod weight 467. Big end, you know, the end where the rod bearing goes. 467. No, total rod weight is not 467, it's 657. Rod bearing. Piston 456. And 129. Locks are 4. This is in grams, by the way. Rings 49. Support rail. That goes under the oil rings because the wrist pin is so far up in the piston. It actually here. Actually, I'll just show you. You notice how the wrist pin comes up into the oil ring here. So in this area of the piston, there's no support for the oil ring. So there's a support rail, which looks like this. It's a sturdy ring, and the only thing it does is supports the oil rail, or the oil rings. And that thing weighs 8 grams. Wheel weight, we'll just call it 5. So, our total bob weight needs to be 1865 grams. That's 932 and a half per half. Now, when I say that, what I'm referring to is, here's a bob weight. You'll see this in a bit, it'll make more sense, but this clamps onto the rod throws or the crankshaft, and together this whole thing needs to weigh 1865, but we weigh them individually, so per half 932 and a half. So these are our weights. We just need to stack these until this whole entire thing weighs 932. And we're going to do that now using the shadow graph scale. It's 100 years old, but it works really well. It's actually really accurate. It's not actually 100 years old, but it's pretty freaking old. So we're going to set this up for 932 and a half. That's 500 grams. Another 200. 700 grams. 8, 9, 32, and then I'll read the half a gram here. You probably can't see this, but just for So the last balance job, the bob weight was actually pretty close, so we're not going to have to add a whole lot of weight. When you're weighing these, don't forget to set this guy on the scale. You'd be surprised how easy it is to do that, to forget to include that guy. Now we've just got a whole bunch of these, I think like 5 grams or something like that. So we need 2 more grams, and if I add another one, that's going to throw us over. So, yeah, that's more like 6 grams a piece. So we've got these smaller guys. They pretty much just look like washers. And they weigh, there we go. That's exactly, that gave us 2.5. That's exactly what we need. So put this guy together. And then I always like to set it back on there and check again just to make sure. So that's 1/2 of a bob weight, 932.5 grams. Then we do the other side. Alright, so that's the other half. So now, together, when we bolt these onto the on the throws of the crank, the whole entire bob weight is going to weigh 1865. And all this is doing is simulating the weight of all the moving parts. Obviously we can't spin the crankshaft in the balancer with pistons and rods connected to it, so that's what these are for. Do that 3 more times, and we'll have all 4 bob weights. Put the crankshaft in the balancer, put the bob weights on, and then we can spin the crank and see how much material we have to remove from the counterweights. When setting the crankshaft up in the balancer, we need to set the 0-degree position of the crank. This is when the first rod journal is in the upright position. When at this position, we simply tell the computer 0 shaft. Now the balancing program knows where the crankshaft is in terms of rotational degrees. With the crank at 0 degrees, we install the first bob weight on the first rod journal. Since this is a Chevrolet crank, this journal is for pistons 1 and 2. Before tightening the bob weight to the journal, we level it using a small level. Next, we rotate the crankshaft to what the computer will see as the 270-degree position. Install the next bob weight on the piston number 3 and 4 journal, level it, and continue. The third bob weight will be installed and leveled on the number 5 and 6 journal at 90 degrees. Then finally the fourth on the 7-8 journal at 180 degrees. At this point, for every 90 degrees of crankshaft rotation, one of the 4 rod journals will be in the upright position, with a bob weight installed and leveled. Finally, it's time to spin the crank for the first time. After the first spin, the computer will tell the operator what the imbalance weight is and where it is in terms of degrees, referring back to the crankshaft position we established earlier. In this case, the crankshaft is brand new and has never been balanced. That means we will need to remove weight from the counterweights. So, how do we remove weight from the counterweights? Simple. We drill into the counterweights. Actually, it's a little more complicated than that. One thing the operator needs to take into consideration is how much weight will be removed if a hole of X diameter at a depth of Y is drilled. For example, generally speaking, if one were to drill a hole with a diameter of a ½ inch at a depth of a ½ inch, the gross weight of removed material will be around 12.6 grams. However, as we are drilling into the counterweights towards the center line of the crankshaft, the deeper the hole is drilled, the less effective the material removed will be. In other words, just because we physically removed 12.6 grams from the counterweight, the effect on the imbalance will be less than that. Balancing can become very involved and complex at times. It gets less difficult with experience. The software will suggest where, how deep, and at what diameter to drill into the counterweights. However, it is up to the engine builder to make these final decisions. Oftentimes, where the software will suggest a hole to be drilled, there will be an existing hole or a piece of heavy metal in the way. When this happens, the operator will need to vector around the obstacle. There will also be times where the computer will suggest a hole location that is completely off the counterweight. This greatly complicates the job. In some cases, we will need to add weight to the counterweights. This is done by adding Mallory or heavy metal to the counterweights. This is completely different and more involved of a process. I will save that for another video. The crank will need to be spun several times, taking varying amounts of weight out of the counterweights as the imbalance values and location change. In the end, we try to have the imbalance down to around ½ gram. Whether it be a 100 horsepower 4-cylinder daily driver engine or a 1500 horsepower all-out race motor, we hold to the same standard. I hope you enjoyed this video.